Okay, go ahead.
Okay, so let's get started. We'll continue our discussion on NP completeness. Basically, we will complete the proof of the Cook-Levin theorem from last time. So we were in the midst of proving the statement Cook-Levin theorem that SAT is NP complete. And what does this mean? We wanted to show that for basically this is statement, what do we need to prove for every language in NP, L is polynomial time reducible to SAT. This is what we need to show. So what we did, I'm just recalling what we did towards the end of last lecture, and then we'll get to one. Then so we took some language L and NP. Now what does this mean? That is, there exists a Turing machine M and two polynomials P and Q such that X is in L if and only if there exists a witness U of length at most polynomially longer than the input length of X such that MXU, M on the pair of inputs accepts, and furthermore that M runs in time Q to the mod X on input X. This is what we had. We also made, I'm going to go a little fast at the beginning because these are things that we did last time, but please feel free to stop me. We're going to make we made some assumptions on M, and these assumptions are justified because of what we did the previous lectures. We had one assumed M was a two-tape Turing machine. Two, that M is oblivious. Okay, that's one assumption to make. And as a notation, another thing I'm going to be using throughout this is I'm going to call M's input. What is M's input? M's input is not just X, it's the pair X and U. So M's input is what? It's this pair X comma U. It's both the actual string from which we are reducing from and the witness. That's the M's input. We will refer to this as Y. Y is going to be the notation I will use. So this. And we're going to use this notion of a snapshot. What was a snapshot? So because it's a two-tape Turing machine, it comes, there's the input tape on which X and then U is written. And then there's one work tape. And the head is reading something here and something here throughout the entire thing. The head is in some state Q. So snapshot is, in some sense, the view of the head of the Turing machine. So it's an element of, so a snapshot is an element of Q cross gamma, where Q tells you which state the head is in. Gamma is what is the symbol under the head on the input tape. The first gamma, so it's something of the form. A typical snapshot has three. It's Q comma A comma B. So it tells you what is there in the this is which head. What's the position of the head? What's the state of the head? What symbol is out here and what symbol is out here under the head. So this is what we had. So stop me if you don't follow the thing that I'm doing right now. And then we had said that for each time step, we're going to define these two functions.
Just one question.
Sure.
Yep. So these assumptions mean that even if you are given a k-tape Turing machine or a non-oblivious Turing machine, you can in polynomial time it can be converted to a two-tape oblivious machine, and then the rest
Yeah,
of
and then do it. In fact, it's not even polynomial time. It's in time just dependent on the description of m, which is a constant, which has nothing to do with the input x. So you take m, you massage it to this one. This is what the two claims which we did in the first or second lecture sort of proved. So it's not, yeah, it is polynomial time, but I really don't care. It's polynomial time in the description of m. M is the description of m is constant. I don't care how long you take in it. So you move from that m to you move to this m.
Okay.
So in fact, you don't even have to do that, because you know if L is a non-deterministic Turing machine, L is accepted by this one, it's also accepted by this. So I'm going to take this particular M to work with.
Yeah, but if you're really constructing an algorithm to do this, then we'll be doing that, right? Yeah.
No, what is the input to the algorithm? The input to the algorithm is only the input X, not M. If M is also the input, you're constrained to do something polynomial time. For example, so M is not an input to the algorithm. M is a fixed thing for the entire reduction. You're fixing one M. So once I fixed L, I fixed M. So now I know that such an M exists. I'm going to work with this M.
Okay.
The fact that we could do it in polytime is good, but that's not going to be essential here. There is a fixed M, which is some constant description of the very fact that L is in NP tells you there is such an M. Claim 1 point, those two claims tell you there's an M with these two additional properties. Okay. And this is a fixed M for all input lengths. It's not, no, it's sort of like, so when you say you want to have an efficient algorithm, there are two things. One is what is the information you have before the algorithm. Efficiency is based on the input length, input given to you. M is not the input to you. X is the input to you. So you have to be polytime efficient in terms of the input, not in terms of these other extra factors. Of course, these could be very large numbers, the description of M, but it's one fixed constant. Yeah, am I making sense?
Yeah.
Okay, and then we had defined these two towards the very end of this one, these two functions for each time step t. We want to define these functions called prev t and input position t. And what are these? Prev t is defined to be the previous time step at which, so the head is moving, the head is constantly moving on both the input tape and the work tape as the machine progresses. What does prev t say? So if you're at a particular time t, it could have been that the head was at that time in the work tape, the head could have been at that position sometime previously also. If so, it is that time. So it's the previous time. Let me write it formally. It's the previous time step t prime at which the head of Tm is in the same position as at time t. And if this is the first, this is bot, or let's call it 0. Previous time, let's call it just an arbitrary, so that you know what it means. So that's prev. This one. And what is input position? Input position I is the location of the head. So this is with respect to the work tape. The head of the Turing machine is the same position as the time t on the work tape. This is just on the work tape, not on the. That's important. That's work tape. And input position t. This is with respect to this one. It is the location of the head on the input tape at time Okay, so this is important. This is the input tape. Now, one easy thing about obliviousness, what does obliviousness buy you? Obliviousness of the Turing machine buys you the following. It says that prev t and input position t are only functions of size of x, which we refer to as n, and not x. So in particular, once you give me the input, you can ignore what the input is. Just look at the location of the input. So can compute prev t and input push t for all t less than or equal to q of length of x, q small q, by running m on a trivial input of the same length, say 0 to the mod x. So you just ignore what you run the input on this length, you find you record it. You just make one run of the input, run of the machine on the input to 0 to the mod x. You just run it on this 0 to the mod x and say 0 to the mod p mod x. So put the other, this is the x part and that's the u part. Just run the machine on this one, and record as it keeps going. You can keep saying prev 1, input pos 1 is this, input pos 2 is this, input pos 3 is this. You just record this whole information. And then you can also do this for prev t. At every time you write a work tape, go to your work tape, find out what time you have gone. Next time you come there, so now you know prev t, what is the previous time that you have come. So you just keep doing this. So you can do this by just running m on this, by doing one single run. So let's assume we have all of these numbers. You can do this in polytime. In fact, it's in time, which is just one run of a Turing machine on a trivial input. You can compute all of these. So let's assume we have all of these in our hand. Now comes the question which we were sort of talking about last time. So suppose you are at zt is snapshot at time t. So zt has three qt, at, and bt. So that's the input tape. That's the work tape. So let's suppose I want to find a snapshot at a particular this one. I need to know what this AT and this BT is, and head QT. So to know QT, what do you need to know? So what are all these functions of? Last time we had said that ZT. So I need to know ZT, I need to know QT, I need to know AT, I need to know BT. I need to know these three things. So where do you get QT from? What is the current? For this, I need to know what happened at the previous time step. So in particular, notice that QT is going to be exactly delta of ZT minus 1, but just take the first coordinate of it. Delta is a function from Q cross sigma square to Q cross sigma cross LRS square. So QT is just the first coordinate of this function. What about AT? What is AT? AT is what is there in the input tape at position time step t. So I claim is just has to be y input position t. That's the definition of input pos t. It's the location there, and therefore it is AT has to be exactly input pos t. Y at input pos t. Is that okay? And what about BT? BT is what was written. Either it's a blank symbol if this is the first time you're coming to the work tape, or is what was written there when the previous time the head was over there. So what would this be?
ft minus 1.
Prev.
Sorry, Satyajit, I can't hear you.
ft minus 1.
Prev t minus 1 is a lot of information. So it will be actually delta of z of prev t, but the second coordinate of it. That's what's going to be written there. So these are what. So I'm going to put up. Notice that so I'm going to write all of this in one combined thing. Say that zt is a function of zt minus 1, y input pos position at t, and z prev t. That's just, it's some such function. So this is how, so if you want to look at the sequence of snapshots, you start with some initial snapshot, then you move to another snapshot z1, then you move to another snapshot z2, and so on, all the way up to zq of mod x. You need to move this. So actually, let me, for notation convenience, I'm going to call this t, and as part of my notation, I will use t to be q mod x. That's the term. So what do we need to know? What do we need to check? That, so I'm going to give you a bunch of snapshots, and I'm going to say you this is the way the head moves, and this is the snapshot of the Turing machine as it goes. And you need to look at this snapshot and say, yeah, when I look at all of this, yes, it's convincing that machine has accepted. So you need to make several checks on this. What are all the checks? What do we need to check? That the above is a valid sequence of snapshots when the machine M is run on input x, u for some u. Probably it was just 0, 1. Okay. What do you need to check? There are several checks you need to check. First, let's check. I want to check that the initial, there will be one check which will be called the initial checks. Let's call it 1. You need to check that the first n bits are actually, first n bits of y are actually x. First n bits of y are equal to x. And I don't care what the remaining bits is, because it could be, I don't care, whichever, as long as there's one u that satisfies me, I'm good for this one. So first, this one check I need to check. The initial snapshot z0 is initialized correctly. Then you need to check the transition checks. That is, for all I, for all t in 2 all the way to t, you want to check that zt is in fact obtained correctly from zt minus 1, y cos t and z rev t. Check that. And finally, you need to check the last one, the final acceptance check. That is the final state, the final snapshot is correct, is accepted. If you make all these checks, then you know that the machine is, in fact, has accepted the machine M on input X and some U has gone through a sequence of accepting steps and finally accepted it. This is what you need to know. Question is, can I write all of this as a CNF? Can I encode all of this? Now I claim that what we know about this one, so let's look at this. So how long does it take to write? So I'm going to write it. So we want to encode all the above. Encode the above as a CNF. And first let's write, what are the variables of the CNF? The variables of the CNF. So as a CNF says some phi of x. What are the variables of phi of x? The variables of phi of x are going to be the various snapshots z1, z2 up to zt, and y1, y2, y p of mod x. Let's just call it y of p of mod x actually. Those are all the variables. This one. These are the variables of this one. And what's the CNF? I want to say now I can write various checks on it. What's the check? What check can I write here? I need to check that the first n bits of y are equal to x. This is something we know how to do. This will take some order n CNF clauses. Order n clauses, you can do this. The next one, initial snapshot is initialized correctly. That's a constant. You just need to check some constant thing. That's an order 1 operation.
The first word is sort of like y1.
Sorry, Satyajit, you are not loud enough. I can't hear you.
Can you hear me now?
Yeah.
Is y1 equal to the first bit of x1 of x?
Yeah, y1 equal to first bit. y1 equals x1, y2 equals x2, y3 equals x3, yn equals xn. This is what we need to do. Okay. And we saw this that it can be done.
Yeah.
Now, what about this guy? This is the most complicated thing. But notice this is just some function. This is just some function on 0 to the, say, how many bits are there? There are some 3c plus 1 to 0, 1. I just need to check that this function, where c is the number of bits required to encode a snapshot. Because this, I want to check this function. This function is going to take 3 snapshots, zt, zt minus 1, z prev t. It's going to take those 3 snapshots and this one extra bit and check that things are fine. It is some function of this form, 3c plus f. So this function is a constant, it's a function on constant number of inputs. We know how to take any function, convert it to a CNF. So we will write, for each of these functions, we will write the function phi f. We'll write a phi f for each time step t. And then once again, the last one is again an order 1. This one. So therefore, the total size of the CNF constructed is how much? It is order n plus order 1 plus t times order 1 plus order 1. So it is something like order t plus n. So now this is the final CNF which we are going to construct. This is the final CNF we'll construct. And if this CNF is satisfiable, it should be evident that The way we are checking, this CNF is satisfiable, that means all the checks are passed, that means the machine has accepted, that means there is a U that caused the machine to accept. So all of this just translates to state that X is in the language if and only if this CNF that I constructed is satisfied. What was key to doing this? What was key? So previously also I said power of C. We use the power of CNF. We use the power of CNF to say that any function can be written as a phi over here. This is what we use the power of CNF. We did the same thing argument last time, but somehow that did not work out. Something became exponentially large. What was the fact?
We didn't use the U.
We didn't, no, okay, we didn't use the U, but there's something more, this one about it. That is, the fact is, computation is a very local operation. This step, if you look at over here, it's a very local check. It's checking, it's seeing something locally, making a check. And computation is just an and of several, it's just do a one local operation, then a next local operation, then a next local operation. The transition function is a very, very local thing. So computation, the key, actually, if you carefully look at the proof, the key to the proof is the fact that each step of computation is a very local operation. In fact, it's a constant sized operation. Is local. And that's important. That was what actually saved us, constant sized, in fact. Computation is local. You do a big global function. You're computing a global function of the input, but every time step you do something locally. And this is already inbuilt in the definition of Turing machine. The Cook-Levin theorem captures this in a very nice fashion. It says because of this, the number of clauses are exactly the number of time steps times some constant. That constant could be a bad constant, but that constant only depends on how local each operation is. The operation is, it might depend on the states, the number of states, this one and all of this, but it's some local, it's some constant sized object. Any questions? Therefore, the final phi-x, so phi-x is going to look like this. Phi-x is going to be this. It's going to be, and there's the initial, there are the clauses correspond to the initial steps. There's one, then there's an and going from 1 to t, corresponding to each of the transition checks. And finally, there's another, the final step. So that is going to be the entire CNF. There are a lot of clauses over here. There are t clauses, but each one of these is a so this one has, n clauses in it. And then each one of these is just constant. Any questions?
So trying to understand this local thing more. So this is true for this machine which runs in, which is for language in NP. So does this ever stop being true for some other complexity class?
No. So what we have proven is not something specific to NP at all. It's true to do with any non-deterministic Turing machine. Firstly, this local thing is true of any Turing machine. The notion of a Turing machine capture, the transition function is a local operation.
Right.
Any Turing machine has this. Where is NP coming here? NP is coming here is the guessing of the U. The guessing of the U is what is making the problem. So it's not just a Turing machine, it's a non-deterministic Turing machine because U is being guessed. Then the entire input is not given to you, only part of the input is given to you. That's why it's a non-deterministic Turing machine. But besides that, there's nothing about NP. In fact, if you stare at this proof carefully, in fact, you don't have to stare at it. If you plot this proof, what we have shown is actually, we have given, this is one of the remarks I wanted to make. The proof is a little more general than what we wanted to say. I wanted to do it later, but let me make the remarks right now. What we said that this is what did we say? We gave a reduction from L to SAT for every L in NP. But actually, the proof shows something stronger. It is a reduction from L in n time Tn. Any Tn. This Tn need not be polynomial. reduction from n time tn to sat with two features. What is the reduction runs in time? How much time does the reduction run? How much time does the reduction take?
T plus n or something like that.
So it's basically t log t. You have to n time t, therefore you have to first convert it to oblivious. That makes it t to t log t or t square, whichever one we thought. And then you run this whole thing. So, and then you have to do one sweep to calculate input position pref t, that's 1 t log t, and then another of all of these. So basically you're going to run, it runs in time order t log t plus n, but whenever we say tt is always greater than n for us all time constructible t. So if it's order t log t. So in particular, the formula size of phi x. So this need not be a polynomial time. It depends on what t is. But because it's NP, t was polynomial, therefore the reduction was in polynomial time. But what we have proved is a very generic statement. From n time t, we have reduced it to sat, and the running time of the reduction takes t log t, and the size of the sat formula is at most order t log t, or t square if you didn't want to the t log t, if you assume this theorem, which I did not prove in the first lecture, we proved it with t square. So it gives you it takes any problem in n time t, converts it to a formula of size at most t square, and the whole reduction runs in time t square. And this should answer your question, Varun. In the sense, this is not specific to anything to NP or something. It works for any n time t. T could be as large as possible or as small as possible, and you always have this reduction. And we'll use this later on sometime. The fact that the Cook-Levin theorem actually gives you the stronger reduction than what we have seen so far. Any more questions? So that's one remark I wanted to make. So it's a reduction from sat t, and that's this one. We find formulas. What about, there's another remark I want to make over here. Let's look at what's happening. So once again, we reduce the L to take 3 sat. We gave a reduction from x to phi of x. That's what the whole reduction did. But at the same time, it did something. Suppose I gave you a witness u here. From that witness, so this is, suppose it was a satisfying witness for this. From that witness, can you pull out a satisfying assignment? For phi of x?
Yes.
Why?
We can run it on m on x dot u.
Yeah, so exactly. Once I give you a satisfying witness, I run m on this one and I write down all the snapshots. Those snapshots and the y that I have there are the satisfying assignment. But I want to say, actually, it goes the other direction also. I give you a satisfying assignment. You can pull out a satisfying witness. Every satisfying assignment corresponds to a satisfying witness. In fact, there's a one-to-one correspondence. This proof, it's not only a mapping between instances to instances. It's not only a mapping between instance to instance, it's a mapping between satisfying witnesses to satisfying assignments. In fact, this reduction also, in fact, it's a one-one mapping between satisfying witnesses of x and satisfying assignments. If there are 10 different satisfying witnesses for x, you can produce 10 different assignments for phi of x. And similarly, if you have 10 different assignments for phi of x, each of them will correspond to one satisfying witness for x. This was not, we didn't want the reduction to have this property. This was more than what we wanted, but the reduction does have this additional feature. And such a feature is what is If a reduction has this extra property, then it's called a parsimonious reduction. The parsimonious reduction is a polytime reduction between problems in NP such that there is a bijection between satisfying witnesses of the start of the source instance and the target instance. Source and target instances. Okay. So this gives you the text.
So when we reduce SAT to say independent set and these things, they were also parsimonious reductions, right?
Were they parsimonious? So 3 SAT to independent set, if you stare at it carefully, that in fact was it a parsimonious reduction? Yes, it was. That particular reduction was a parsimonious reduction. So I'm going to give you another reduction just now, and let's find out if that's parsimonious.
And what about integer linear programming?
Integer linear programming.
Yeah, that was, yeah.
I think that also there's
That
a bijection between them. Yeah. So a lot of these reductions have this extra feature. This is something which we do not want of. We did not want of the reduction, but the reduction had this property. Later on, much later, when we're counting problems, we will actually use this fact that the Cook-Levin reduction was parsimonious in our favor. Okay. Any other questions?
So x can be mapped to various phi x's.
No.
But the function is
X is not mapped to this. Reduction maps x to one phi of x. So it looks like this. So this is the set of instances for L. This is a set of instances for SAT. L is sitting over here. So this is 0, 1 star. And these are all SAT is sitting over here. So X is being mapped to X in the language is mapped to phi of x here. X outside is being mapped to an unsatisfiable phi of x. But it has the property that if X has 10 satisfying assignments and 10 satisfying witnesses, phi of x has 10 satisfying assignments. There's a bijection between the reduction only wanted things inside to go to things inside, things outside to go to things outside. But it has this other feature that it's not only a mapping between the instances, it's also a mapping between the satisfying instances for x and the satisfying instances for phi of x. Every x is carried to only one phi of x, this reduction, the way the reduction operates. Does that answer your question, Roshan?
yes.
Okay. Any other questions? Okay. So, by the way, to do the reduction to independent set, the starting point, was it SAT or something else?
We started with SAT, I guess.
We started with 3 SAT, not with SAT. Right now, I've reduced only to SAT. So I need to further show that 3 SAT is NP complete. For that, we needed to know 3 SAT. The next step will be actually. So Cook-Levin theorem, we need to prove. We'll now prove that 3 SAT is NP complete. And we'll prove that by giving a reduction from SAT to 3 SAT. So you give me any CNF, this one, I will convert it to another CNF. So basically, I give you a CNF phi. I have to convert it to another CNF psi, such that this is also a CNF. This is a CNF, but furthermore, this is a 3 CNF. That is, every clause has at most 3 variables. Okay. How do we do this? So let's take, say, phi was C1 and C2 and Cm. What we are going to do is we're just going to make one pass on this, and we are going to convert this into psi1 and psi2 all the way up to and psi_m, using the same variables or more variables, such that each psi_i is a 3CNF plot, a 3CNF formula. So we'll take every clause of the original formula, convert it to another clause on the same number of variables, with the same variables or possibly more variables. So what will that be? So Ci to psi_i.
There isn't a blow up in the number of clauses or anything?
No, there is, because each clause is being mapped to a formula.
Okay.
Each clause is not mapped to a clause.
Okay.
Each clause is mapped to more than one clause.
Okay.
That's why in the starting, this might be a clause, but this is going to be a formula. But it will be a 3CNF formula.
Oh, Saya is a 3. Okay, yeah.
Each Saya is a 3CNF formula. It's an AND of several 3CNF formulas, it will still be a 3CNF formula. So how do we do this? If the number of literals of psi_i is less than or equal to 3, then of Ci is less than or equal to 3, this can be just Ci itself. There's no one. Now you look at the other case. Say the number of literals of Ci is greater than or equal to 4. Say, let's take one example. Ci, say it is L1 or L2 or L3 or L4. I need to come up with a formula such that that is satisfiable if and only if Ci is satisfiable. And I claim I will do this. Take Ci, I'll define it the following way. L1 or L2, I'll bring a new variable Z. Z complement L3 or L4. Now, no matter what Z is, if Ci was satisfiable by a particular choice of variables, no matter what Z is, Psi I is satisfiable. If Psi I is satisfiable by a particular choice of variables to L1, L2, Z, L3, and L4, no matter what value Z has, Ci is satisfiable by the same choice of assignment to the literals L1, L2, L3, L4. Because either Z is 0 or 1. If either Z is 0, L1 or L2 is true, in which case Ci is true. If Z is 1, then for this clause to be true, L3 or L4 has to be true, and hence this will still be true. Okay, I could do it for 4 clauses. What about for 5 clauses? Suppose it was L1 or L2 or L3 or L4 or L5. You can do exactly the same thing. You'll bring L1 or L2. I'll bring a Z1 variable, then Z1 complement or L3 or Z2, Z2 complement or L4 or L5. So notice that this will be my Psi I in this case. Notice that if L1 or L2 or L3 or L4 or L5 is true, either L1 or L2 must be true, or L3 must be true, or L4 or L5 must be true. Depending on which one of these, you can set Z1, Z2 correspondingly in the right way so that this becomes true. Similarly, if this is true by a particular assignment to L1, L2, L3, L4, L5, and Z1, Z2, then the same assignment to L1, L2, L3, L4, L5 will satisfy Ci. That's all we do. So we just take, in fact, notice that this is an extremely simple reduction. It takes a particular clause. If the clause has more than 4 variables, it just blows it up like this. It's a linear time reduction. It's just going to do this and produce this. So this is the reduction from SAT to 3SAT. Okay? People follow me?
So there's an and, right, in all of these, like
Yeah, there's an and. Whenever I don't put anything, there's an and. Yeah.
So the blow up is linear to the number of literals.
Blow up
N
is
minus
linear to the number of literals. So
n
the
plus 2 or
original-
something.
Yeah, if it was m, this I think it's no, it's actually if the original literals was m, this will be the number of things will be I think m minus 2.
Yeah.
M minus 2 will be. Therefore, the number of clauses will exactly be the number of 3CNF clauses that we will have will exactly be, it will be something of a function of the total number of literals of the original number of literals in CI, where literals are counted with multiplicity. In phi. Okay. So if you stare at this a little carefully, this is not a parsimonious reduction. Huh? It's a good exercise to make it a parsimonious reduction. It's not a parsimonious. There's not one. This is not a parsimonious reduction. The way I have done it, it's not a parsimonious reduction. But you can make it a parsimonious reduction, and I will leave it that as an exercise. Any questions? So, not
Did
really.
it anyway establish that every non-parsimonious reduction can be like converted to some parsimonious counterpart or something like that?
I don't know about that. That seems too general a question. At least for all, because Cook-Levin theorem gives you a parsimonious reduction. For all problems within NP, we do have at least the reduction from any problem. This one to SAT is parsimonious. So as long as we do not know, if you give me two arbitrary problems in NP, I do not know. If you tell me the target problem, what it is, then you can ensure it's parsimonious just by taking the first step to be the parsimonious reduction of Cook-Levin, and then construct a tailor-made parsimonious reduction from SAT to your specific problem. For almost every such thing, I know how to do it, but I don't know a generic statement of how to do this. So in particular, I can do it for every such problem I know of. I know how to construct a parsimonious reduction. I don't know a very general statement that you can make things into parsimonious. By the way, notice a reduction is true between any two languages. But to talk about even parsimonious reductions, I have to talk about languages in NP.
Yeah, right.
Okay.
The reason why this above reduction isn't a parsimonious thing, because we don't know if even if we are given CI, the literal satisfying CI, we don't know about anything about Z1 or Z2, right?
There could be multiple Zs that cause even if there was one setting for the literals L1 to L4, L5, there are multiple Zs which will turn this on.
Maybe exponential number, I guess.
Once there are multiple, possibly there are many, but you can put some more conditions on Z to make sure that that does not happen.
Okay.
It's not hard to see that, but I might toss this in as a homework problem or as an eventual exam problem at some point of time. But it's a good thing to notice how to convert this into parsimonious.
Yeah, okay.
Reduction. Okay. Okay, so the next thing which we're going to talk about is SAT. So fair enough. So we showed that to show that so we had this world of NP problems. We had this language of NP, and there were these nice problems called SAT3. Some subclass of this was P. And then there are problems here which we believe are not in NP. 3SAT, vertex cover, independent set. These were a class of NP complete problems. A bunch of them were NP complete problems. And this whole thing said that if any one of them falls into P, it brings with it the whole class NP into P. That's fine. So in other words, if any one of them, so tomorrow suppose somebody comes up with an algorithm for vertex cover that says that SAT has a polynomial type that is given a formula, you can check in polynomial time if it is satisfiable or not. What I would want is not just satisfiable or not, what I would want is actually to compute a satisfying assignment. So does P equals NP? The question we are going to ask now is suppose P were equal to NP, then can check if a formula is satisfiable. Can we also find a satisfiable assignment if it is if one exists in polynomial time. So that's what. So suppose I tell you, I give you an algorithm that tells you, given a formula, to check if it's satisfiable or not. Can you use this algorithm to actually find out a satisfying assignment?
So maybe I can like put
So
an X1 as
just once the one says, so the question, you can also train for one. Suppose I give you a vertex cover independent set problem. That is, I tell you that I give you an algorithm which will tell you, given a graph G and a number K, it will tell you if there's an independent set of size larger than K or not. Using this, can you use this to construct an independent set of size K? So this is the what I'm going to call the search versus decision question. Okay, sorry, go ahead, Satyajit.
So like for SAT, maybe like you can put like x1 equal to 0 or x1 equal to 1 and maybe then check whether it is satisfiable.
Yeah, so let's look at the specific case of SAT. So suppose we'll exactly do what was suggested. So I have phi. Now I have an algorithm that solves satisfiability. So I know it is. So if it's not satisfiable, then there's no point of searching for a satisfying assignment. Suppose I know it is satisfiable, then I know one of these two things, either phi when x1 is set to 0 or when phi x1 is set to 1 is satisfiable. So once you know phi is satisfiable, you have one of these is satisfiable. So you now ask the algorithm one of these two things. You ask the algorithm, is phi of x1 equals 0 satisfiable? If it is satisfiable, you know that there is an assignment which extends this. If it is not, you know this one is satisfiable. Now, once you know this is satisfiable, so you can then further go and ask, is the formula x1 equals 0, x2 equals 0, is that satisfiable? So possibly the algorithm returned the answer yes over here and no over here. And here you went, it returns no over here. That is, it's not satisfiable. So you can now once again come here, you can try this one. So you know that this one is satisfiable, x1 equals 0, x2 equals 1. So this has to be satisfiable if it had given. So you sort of walk along this tree. You just keep walking along this tree. Notice that the whole tree is exponential sized, but you're not navigating the entire tree. You're just walking along a path of the tree. You're finding out each time which path to keep navigating, and in fact, you're finding out the leftmost path of the tree. You're not navigating, if you're doing this, you're finding the leftmost path. And so this is what is called. So the end of this, what I claim is the following. We have the following statement. That is, if P equals NP, then there exists a polynomial time algorithm that, given there exists a polynomial time algorithm for every language in NP, that when given an instance X, checks if X is in the language. This is certainly can do. And if so, finds a satisfying assignment, finds a satisfying witness. I'm writing this for every problem in NP. What I showed above does it only for SAT. But now you use the parsimonious reductions of Cook-Levin. Any problem in NP, first reduce it to SAT, do this, and at the end of it, you get an assignment for SAT. And then from that assignment, you can pull back a satisfying witness for the original problem. Okay, so P equals NP not only solves the decision problem, it also solves the search problem. Okay. And one other feature of this thing, if you notice it, what is it saying? So suppose I told you that I could solve SAT on all formulas in which the number of variables is at most 10. Does this mean that you can now solve SAT on all variables of formula of size at most 11? Sorry, let me state it again. Suppose I tell you I can solve SAT on all formulas which have at most, say, 1000 variables. This process is actually telling you, using this, you can solve SAT on all formulas that solve it on at most 1000 plus 1 variables, because you can reduce. So if you gave me if you know how to solve SAT on formulas with a particular number of variables, you could use that algorithm to solve SAT on one more variable. That's exactly, this is stating that if I could solve these two cases, then I can solve this case. And this is what is called the downward self-reducibility of SAT.
So Prahladh, in this there is a factor 2 overhead, right? Because you are reducing it to 2 separate instances of the smaller net.
Yeah. So if I can solve it on a smaller instance, I can solve it on the larger instance at a blow up of a factor of 2. If I didn't have this, but Ramprasad's point is important, because if I didn't have this factor of 2, then certainly I can solve SAT on one variable. You can use that to solve SAT on 2 variables. You can use that to solve SAT on 3 variables. You can keep going this. The point is, what's the extra blow up each time? Each time the amount of time doubles. So it eventually becomes 2 power n is the number of this one. If this was not doubling, if it was only if the blow up was just an additive constant factor each time, this would be really great. This would give you a polynomial time algorithm for SAT. In fact, I think it'll give you a linear time algorithm for SAT. We don't know how to do this, but SAT does have this downward self-reducibility. Basically, I'm going to be very informal here. I'm going to say that in some sense, T of n is less than or equal to some 2 times T of n minus 1 plus some, say, order 1 operations, where T of n refers to the amount of time required to solve SAT on a formula of size with at most n variables. This is what is called downward self-reducibility. And it's, by the way, the fact that SAT has downward self-reducibility is a very useful concept. If you started doing the problem set, you would already need this for a couple of problems. And it's downward self-reducibility of SAT, which lets you to go from the decision version to the search version. Any other questions? Okay. So if that's done, we'll move to some related topic, also related to NP, but talk about what's called coNP. It's called co-non-deterministic. So coNP, one way of defining coNP is just take all languages, take the complement of all languages which are in NP. Oh, notice this is a complement of languages in NP. It is not the complement of NP. It's not the complement of NP. It's a complement. The languages in coNP are languages whose complement is in NP. You're doing complement language by language, not the complement of the whole class. Okay, this is just a syntactic definition, but I want to say there's another way of it. So the nicer definition of coNP, what was NP definition? There exists a satisfying witness that convinces you that the string is in the language. This is exactly the other way around. It says language L is in coNP. If I'm just unraveling the definition of NP and this complement going on, if there exists a Turing machine M and polynomials PQ such that X is in L if and only for all U in 0, 1 to the P mod X, mxu is equal to 1 and m runs in time. Runs in time q mod x on input x comma u. Okay. So coNP is exact. NP was in which if you to show membership, it's sufficient to give me a short proof, a short this one. coNP to show non-membership, to show something is not in this language, you can give me a short proof. So if suppose you give me a u such that mxu is 0, that proves to me that x is not in the language. Because if x were in the language, every u will show mxu will be equal to 1. So in other words, main thing here, NP is which there are short proofs of membership. NP is exactly those languages which have short proofs of membership, whereas coNP is exactly those languages which have short proofs of non-membership. And the classic example of a problem in coNP is what's called tautology. What's tautology? Tautology is a set of all formula such that phi is always true. Examples say x or not x. So why is it in coNP? Can you quickly tell me why it's in coNP?
For all 0 and 1, it's always true.
Always true. Can you go by the previous thing? Is there a short proof of non-membership? If something is not a tautology, how do you show? What's the short proof that it's not a tautology?
Proof of unsatisfactory like resolution or something like resolution.
No. What is a short proof? I don't want to asking you how to land on the short
You
proof.
just need one witness, sir.
So give me some witness that shows that the formula is false. Just like satisfiable, there was some witness that the formula is true. If you give me some for non-membership, all you need to show is there is some witness, some assignment on which the formula is unsatisfied. So if you give me a violating assignment, that is the short proof. So tautology is exactly in which non-membership in tautology, you have short proofs. Membership, I do not know how to prove, but non-membership. Notice here, tautology is exactly those problems for which showing that it is not in the language, I can give you a short proof. I don't know how to come up with a short proof, but I can. But once somebody gives me a short proof, I can easily verify. SAT has exactly the other feature. That is, if the thing is in the language, then there is a short proof. I do not know how to give short proofs of non-membership for SAT, but for membership, I can give you short proofs. I don't know how to come up with the short proofs, but there is always a short proof that convinces me. This is the thing about NP. NP is you do not know how to come up with the satisfying assignment, but suppose somebody gives it to me, I can check that the satisfying assignment convinces me that the string is in the language. That's in fact the definition of NP, and coNP is exactly the other way. So it's those languages which have short proofs of non-membership.
Yeah. So, like, if we consider the language taught, so every string in zero and star is a SAT problem, right? I mean, we can there's a bijection between every string.
Yeah, you can take every string if it is a legitimate, some encoding of a formula. If it's an encoding of a valid formula, take it. Otherwise, that just says the encoding of the formula true. Yeah.
So consider the language L. L is taught. So that means L complement would be the set of all binary strings such that phi is either always false or phi is true for some assignments and false for some assignments, right?
Yes.
So I mean, it is not obvious that is in NP.
No. But once again, what did you say? So SAT, you took SAT.
Yeah.
And now
I took taught.
Huh?
Yeah. Take tautology.
Tautology is my L.
You're taking tautology, okay. And you're looking at tautology complement.
Yeah.
Huh?
Yeah.
So what is tautology complement?
So set of false strings such that it either is always false or it is true for some assignments and false for some assignments.
So in other words, it is false. Tautology complement is exactly phi, such that phi is false for some assignment. Okay. This is not SAT, but it is. This is tautology complement. Clearly, this is in NP because to show.
Okay, give this assignment.
You give this assignment. That's all.
Yeah.
Yeah.
Okay.
So tautology complement is in NP. You can, if you stare at it both classic, tautology complement is one way of writing SAT, but let's leave it at that. Tautology complement and SAT are actually possibly exactly the same language, but not the way I have written. Okay. Any other questions?
Yeah, if you take negation of phi, then it is true for some assignment.
Hmm?
I mean, if you take any
negation,
phi,
if you do so if from CNF you'll go to DNFs, and if you do negation, you'll get this. It's not hard to see this.
Yeah.
Okay. Okay. So one question. The next thing which I want to introduce, actually it's more to introduce a technique called padding, but I will introduce it by talking about the.
So also I didn't understand the how those two are equivalent. Like
Which
you
two?
said you gave two definitions of coNP.
I gave two definitions of coNP. If you actually look at the definition, I'm just taking this definition and unraveling this definition. I'm saying L complement is in NP.
Yeah.
If you just unravel that definition, this is what you will get. I don't want to say more because I think I made this into a problem set. Problem in the problem set, which is just opening. I almost given away everything here. You just open out this definition. Take the definition of NP, write down what it means, and you will get this.
Okay, is it in this problem set or?
It's in. I think it's in this problem set. No?
Okay, fine.
Yeah. Because I think one of the problems which are devoted to coNP. Okay. So I want to introduce.
Yeah, it's problem 4 in the problem set.
Yeah. But do it while talking about NX. So NXP is just like NP was this definition of NP, which is n time n to the C. It's the union of over C greater than equal to 1. NXP is just, and we thought that this was sort of P was D time n to the C. It also defined X over here, which is D time 2 to the n to the C for all C greater than equal to 1. You can define certainly the corresponding notion over here, which is NX, which is n time 2 to the n to the C. It's a natural definition. What I want to prove, seems as following simple fact I want to prove, is if P equals NP.
Prahladh, could you just sort of give an example of an NXP or something that is an NXP?
If you have done the problems before the.
Okay.
So let me give an example of a problem in NX. So example of. So what was, I'm just going to create an artificial example. You remember TM-SAT. What was TM-SAT? TM-SAT was alpha x 1 power n 1 power t. So that what was it? There exists a u of length such that m alpha xu equals 1 and m alpha runs in time t. This, and what did we show? In fact, we already observed that TM-SAT is NP. It's not just in It's an NP complete. It's an NP complete problem. I'm going to write TMSAT. What I will write? TMSAT binary. It's almost the same thing, in which instead of giving n in unary, I'll give n in binary. N and T in binary, and exactly the same thing as above. I'll copy this later, but anyway, that's the same thing as above. Notice that this runs, this is an NEXP, because what you do, you have n, you have to run in time, you have to first guess a string which is not n bits long, but you have only log n bits, because these two are written in binary. If you open it out, write it down, that's exponential time, you do it, and then do the thing. And you can also check that this is actually an NEXP complete. For the same reasons TMSAT is. So this one is in NEXP and is in fact NEXP complete. NEXP hard. But it's not a nice problem which is NEXP complete. We will later on, I do not know if we'll see, but there are nice problems which are NEXP complete. Okay. So what was the theorem I wanted to prove? I wanted to prove the following fact. Suppose you knew P equals NP. So just like we believe P is not equal to NP, we also strongly believe NEXP is not equal to EXP. So non-determinate. I want to say that actually, if I can show P equals this NP, then actually I can also show X is equal to NEXP. How would you prove this? So actually, the reason I'm giving this is to demonstrate a technique, a useful technique. Once you know it, it will seem like a trivial technique, but it's a very useful technique to have, what I'm going to call the padding technique. So let's assume P equals NP. Now let's pick any problem L in NEXP. Okay. So in particular, L is in some n time 2 to the n to the c for some constant c. Now I'm going to construct a new language called LPAD, which is almost L, which is X, but I'm going to give it. So the input, I'm just going to pad it with dummy symbols. Sorry, this is not X. This is X to the C, where X is in the language. So take every string in L, just pad it up so that I give a lot of dummy symbols at the end, so that. Why am I giving this? So that I'm increasing the input size artificially. I'm padding the input to increase the input size artificially. Now, where does LPAD lie in? What class does LPAD lie in? L lies in n time 2 to the n to the c. So where does LPAD lie in? How much time does it take? You can use the same algorithm that you had for L, the non-deterministic algorithm, but how much time, how much non-determinism do you need?
It will be in NP.
Huh?
It will be in NP.
It will be in fact, n time n.
Yeah.
Because in the new input length, it's actually linear. The old algorithm is linear in the new input time. This is in NP, which is a subset of P by assumption. So LPAD is in P. That means LPAD has a polynomial time algorithm. Now I want to say that if LPAD has a polynomial time algorithm, what can you say about L? What can you do about L? Can you use that polynomial time algorithm to solve L?
Yeah, you just run it on the machine P.
Yeah. So what you do is you take L, you just go and pad it. Take on input X, you pad. So what? So how this is an algorithm for L is on. I'm not going to write it down, but it's fine. Take the input X from L, you pad it, then run the polynomial time algorithm. It's polynomial in the padded input length, which is exponential in the original input length, but it's a deterministic exponential time. So basically what I'm saying is just on input X, pad it and run the P time algorithm for L pad. Together, if you look at this, this shows that L is in EXP because the padding takes exponential time and then it's polynomial in the new input length, which is exponential. It's polynomial in 2 to the n to the c, which is another exponential. So what have I done at the end of it? So now I have hence NEXP equals EXP. We stare at this. It's a very simple technique. Padding just tells you if there is a complexity collapse happening below, it actually happens above too. So padding is a very simple technique which says that collapses scale up. So in particular, if you show P equals NP, that will show NXP equals PX, NX equals X. It will show non-deterministic doubly exponential time is equal to doubly exponential time and all of these things. And separation. Suppose the contrapositive of this. If you show in order to prove P is not equal to NP, it is sufficient if you show X is not equal to NX. If you show that, that will have to imply because that's the contrapositive of this statement. So separation scale down. It's a useful technique to know. Padding is a very simple technique, but it's a useful technique to keep in mind to move from one complexity classes, equalities and separations in one world to a world which is much higher. So poly time to exponential time, or even from say linear time to quadratic time and all, you will do this. And think that padding is a very simple thing. There's going to be a problem in your second problem set, not the current problem set, the next one, which will use padding in a very ingenious fashion to actually prove it. So padding is a useful technique. Yeah, I won't even say which problem needs padding. I've given you the hint that some problem in second problem set will require padding. And you have to figure that out. Okay. Okay, now I have about 8 minutes. I'll philosophize on some thoughts on NP, NP not NP, P, NP, and the coNP question. So any questions so far? So next 10 minutes is going to be non-technical. It's going to be more. Yeah, any questions so far? Any of the things we have seen? What am I doing? Anyway, so okay, so I wanted to say a couple of things about NP. So what does NP capture? So NP captures these things in which I do not know how to solve the problem, but if somebody solves the problem, they can give me a short proof that convinces me that their solution is correct. NP is exactly these problems. Satisfiability is one such question. Vertex cover was one such question. We noticed that composite was also one such question. Eventually, we realized that about 15 years ago, we realized that composite also has actually a fast solution to show that a number is composite. But most of these problems are things in which there's no easy way to come up with a solution. But once you have a solution, you can give me a short proof that convinces me that the solution is correct. This is sort of similar to, in some sense, if somebody proves to me, I do not know how to prove a math theorem, but if somebody gives me the proof of the theorem, I can check that the theorem is correct. I just go through the proof. I don't know how to compose great music, but if somebody plays good music, I can listen to it and realize it's nice. I don't know how to build an engineering marvel, but when I see it, I do realize that it's sort of good. So this is sort of this one that is actually coming up, producing a solution is much harder than verifying a solution. There's these two different things. Producing is coming up with manufacturing a solution seems to be in various facets of life seems to be a much harder task than verifying a solution. Verifying this is good. And the P versus NP question is sort of a computational version of this question. It is sort of stating it's hard to come up with creativity, but once something is, you can do it, you can convince to me, it's showing that the P versus NP question is precisely the computational version of this question, stating that P not, if you believe P not equal to NP, it is trying to say that trying to come up with a solution is much harder than verifying a solution. And we face this in all facets of life. There are geniuses out there. You don't know how they do it, but when they do it, you do realize it happens. I'm not saying this is the same question. This is the sort of the computational analog of this question. In our language, we are trying to capture this. So NP is not equal to P is sort of a computational version of a much deeper phenomenon that we happen to see quite often in nature. So it's sort of it's a computational analog. The P versus NP question, what I want. P not equal to NP question is sort of computational version of can ingenuity be automated? It's precisely asking this question, but in the computational world. That's one thing about it. So also sort of math theorems are also falling in this one. That is, I do not know how to prove a Fermat's theorem or the Riemann hypothesis or something, but if somebody proves it, there is a shock. I can just go and read in the proof and check that the proof is correct. Okay. While talking about P, we also talked about, then there's this other question, the NP versus coNP question. P versus coNP question says if something can be solved, can it be, if you can find a solution, can you find one efficiently? If you can verify a solution, can you verify it efficiently? NP versus coNP is asking you, so you have tautologies. So let's look at tautologies. Tautology is set of all true things. Do these true things also have, can you prove so what is tautology? So to prove something isn't a tautology, to show something is not a tautology is easy. I just give you an assignment on which it is one. But suppose NP were equal to coNP. That means to show it is a tautology also is easy. Because I can give you if NP were equal to P, if NP were equal to coNP, then every phi in taut has a short proof that it is a tautology. Notice this is a very surprising fact. I don't believe such a statement. We typically don't believe a statement. To prove something is, to disprove something, it's easy. You can give me one example and say this is the reason why it's false. To prove something, you have to show every possible thing is true. But if NP were equal to coNP, this says no. Whenever something, you can disprove it easily, you can also prove it easily. If there is a short proof of membership, there's also a short proof of non-membership. The NP versus coNP statement is basically stating that short proofs of membership do they imply, question is, does it imply short proofs of non-membership? So suppose I can, for satisfiability instance, to show a formula is satisfiable is, there's a short proof. I can give you a satisfying assignment. To show a formula is not satisfiable is, I don't see how to do it easily. I don't see how anybody can give me a short proof that can convince me that a formula is not satisfiable. But if NP were equal to coNP, the statement that we are claiming that is in fact true, that there are short proofs of non-membership. The NP versus coNP question is fundamentally attacking this particular problem. That is, does everything that has short proofs of membership also have short proofs of non-membership? This whole area is quite an active area in complexity, which is called proof complexity. And there's a lot of work that goes on in this particular area, which now doesn't address the P versus NP question, but more addresses the NP versus coNP question. Okay. Now, the other thing I wanted to mention, which we will see shortly in this one, there's this class of NP problems. There was P over here. And then a whole bunch of problems here, we saw they were NP complete. What we do know is even if one of these problems collapses into P, it brings in with it all of NP to P. But you can suppose that were not the case. That is, NP complete is actually all these problems are distinctly. Suppose they were outside. Question is everything outside P NP complete? You could ask that. So, question I want to ask is the following: if NP not equal to P, then is any L in NP minus P NP complete? The answer to this happens to be no. That is, if NP were not equal to P, then there are a lot of intermediate problems which are neither in P nor in NP complete. In fact, there are infinitely many such problems. No, in fact, there are a lot of NP intermediate problems. And we might do this in our next topic, diagonalization. I'm not sure whether we'll have time, but it's an interesting theorem that can do. This is called Ladner's theorem. Okay, it's already 1. I'll take 5 more minutes and wrap up. So that's one. Other is, what happens if? What if? So we're studying all of this. So what if happens if P were actually equal to NP? That means all of these problems that we care about have polynomial time algorithms. So it seems as if it's an algorithmous utopia. That is, everything that you want to solve, you do have polynomial time algorithms. It's not perfect. It's not fully true. It only says they have polynomial time algorithms. It might be that SAT has an n to the power million algorithm. This might not be a very useful fact at all. So the algorithms we run in practice are n square, n cube, n power 4 at most. Even n power 4, you can't run it on a large data set at all. Question then you will be more interested is, you care about, so you're interested in more fine-grained complexity. That's one thing you'll have to begin looking at. What do some of these problems have actually polynomial time, or the exponent of the polynomial is really low. The other thing you would want to ask is, it's not always utopia. All of our cryptography just goes out. Current day cryptography depends on the fact that there are hard problems, actually much lower in NP, much lower than NP, which are hard. Now, if nothing in NP is hard, this is a cryptography. It might be an algorithm's utopia, but it's a cryptographer's nightmare. If this was the world we were living in. Because you can't base anything. There is nothing to base your cryptographic security on. There are no hard problems to work on. Okay, so that's one. So if NP equals NP, this is one. This one. Now you can ask other questions about. Suppose you're working on some problem. You have a formulation of the problem, and you realize that the problem happens to be NP complete. So you're working on a problem. So some problem. So what I want to mention is coping with NP hardness. So you have to solve some problem. You're writing some problem. You write a mathematical abstraction of the problem, and you realize it's NP complete. Of course, that statement of the problem is way too hard. But this is not. We can't stop at it. We want to solve these problems. So what do? find out if your abstraction is so general that it is captured much higher. Because invariably, it's not that you want to solve the problem, you want to solve an abstract problem. You have a specific instance that you want to solve. There's a particular data set that you care for. You want to see if your abstraction is so general that it doesn't that it captures not only this data set, but several other data sets that make it harder. So that's one thing you can do. You can ask, is there a mathematical formulation that makes, has your formulation become so general that the problem has become hard? You can look at that. Other thing is you can think of coming up with heuristics that solve the problem in most cases, not necessarily in all the cases. In particular, on the cases that you care about. Possibly satisfiability is hard on some formula, but possibly problems that occur often in this one. In fact, that is the case. Satisfiable formulas, there's a whole SAT community today which says that most SAT formula that you see are actually you can easily come up with a satisfying assignment for them. Though we know that we believe SAT is a hard problem. Most SAT instances that we do see in practice actually happen to be ones that you can solve it very easily. So you might have come up with heuristics that work well most of the time. That's one way of doing it. Another way of doing it is what is called approximation algorithms. And this is a topic we will come to towards the end of the lecture, towards the end of the course. We'll come to what is approximation. In fact, there'll be a flavor of this in your current problem. I think there is vertex cover. There's one of the problems in the problem set which is talking about an approximation algorithm for vertex cover. With this, I will stop with this. Any questions? Next time we'll go on to CN, something which you might have seen in theory of computation, diagonalization, which is basically try to answer the question: with more time, do you get more power? Suppose I have a quadratic deterministic machine and I give you a cubic deterministic machine. With cubic, can I actually, certainly I can do everything in quadratic and cubic time if I'm given cubic time, but can I do strictly something more? Is there a problem which is in cubic time that I cannot do in quadratic time? And we'll show that is in fact true. With each additional power, with more and more power, with more and more time, you actually get more and more power. You can solve more languages, and we'll use diagonalization to do this. I'll stop with this. Any questions?
Actually, for a cryptographer to have issues if P is equal to NP, then the algorithm should also have a fine-grained complexity, right?
So you will have, so you mean to say cryptography now has to be based on fine-grained complexity hardness and not on this one? Yes and no. Yes and no in the sense that, if P were equal to NP, you have to change all your hardness assumptions in this one. But you have to, I do not know how the hardness assumptions that we have. So there are things called based on ETH hardness. Certain cryptography works, and you'll have to scale these down and work with them. I do not know if so many cryptographic systems are actually work on such fine-grained hardness.
Even the RSA algorithms, won't they still hold if the polynomial algorithm has a time complexity of n power million?
Yeah, your assumptions have to be your assumption. So the point of cryptography, it's not just you. So RSA, you're asking, can now make an assumption that RSA doesn't have possibly RSA has an n to the million algorithm, but doesn't have possibly doesn't have an n square n cube algorithm. You will have to revise your hardness assumption and see whether all those reductions still hold good under these revised hardness assumptions. And I don't think we have studied algorithms from a fine-grained complexity point of view. I don't think we have done cryptography very much from fine-grained complexity. There has been work which primarily trying to talk about basing on ETH hardness and stuff. We'll have to redo all of this. The current belief is that we are not just in P not equal to NP. We are in the world is there are far more hard problems out there, and that's this one we take because that doesn't seem to be a realistic viewpoint that P is equal to NP. We don't know. Yeah.
Maybe just to add to Prahlad's point. So if it so turns out that factoring, for instance, has an algorithm that runs an n to the 100 time, but nothing faster, I don't think that the world will change. I mean, from the perspective of, I don't know, 1000-bit keys or something, you are probably still secure. But normally when you talk about cryptography, there are formal definitions of when you say something is secure. And those definitions will break if you know that your hard problem has a polynomial timer. It's a question of whether practically does it make sense. Maybe it will. But yeah, I mean, it's important that you are on sure footing. And the whole point of theoretical cryptography was that we start having a sure footing for what we do. And those specific definitions will change. And what Prahladh was pointing out was that maybe you'll have to go revisit those definitions and come up with some fine-grained analogs of this.
Any other questions? Okay, conclude the class.